Hello there, so this is the third video on efficiency and I'll actually be going through a Matlab demo. So you can get the code for this demo via a link that's in the description box. So make sure you take all the files that are there because you will need them to rerun the code on your own. So make sure you're ready for this. Do you know what efficiency is? And do you know the math behind it? If not, revisit these two earlier videos, the last two that were posted basically. So the first one talks about estimation versus detection. FYI, we are going to be performing efficiency calculations for detection, not for estimation, today. And the second video is the math behind it, so you can code it yourself. So today I'm basically showing you the code. Oops, we're not done yet. So let's move to Matlab for a second. Right, so this is basically the directory that you'll download from the Dropbox, and you'll need that. And let me describe what we're doing here. So the idea is that we have a paradigm where the subject is shown a stimulus for 2 seconds, then there's a 4-second interval or some type of interval of some duration with a fixation cross, and then they're given a second, a response stimulus basically. So there's a stimulus, fixation, response, fixation, repeat. So the paradigm I'm talking about isn't, it doesn't directly reflect the one that I think I focused on the most in the other lectures where efficiency was improved by changing the trial order. We always need to have the stimulus before the response. But what we're going to do is look at how jittering the interstimulus interval, so basically the time that the fixation crosses on the screen, how instead of making that fixed, say 4 seconds, I'm going to work with 4 seconds, if we instead jitter that so it falls between some range of values, we'll see an increase in efficiency if all goes well. So, and it will, we'll see. So before we get to the code, I want to draw a picture. So this text here is just describing what I just said, but I will draw a picture over here for you. And this, whatever I write, will be in that same Dropbox folder. I apologize, I have a cold, so I'm a little congested. Okay, so here's the idea. We have a stimulus, and that occurs for 2 seconds. And then we have fixation, and the fixation lasts for 4 seconds. And then we have some sort of cue, oopsie, for the response. Where's the thing? Oh, here's the thing I want. And this is also 2 seconds. So this is the response. Where this is obviously fictitious, convenient example. Typically they'd hit a button or something, so you'd be modeling reaction time, but obviously you can't simulate that ahead of time. So anyway, we'll just pretend the stimulus the response is 2 seconds. And then we have another fixation for 4 seconds. Oops. And then the next stimulus occurs. So the entire, if you want to refer to this as a trial, which some people use that terminology, we'll call this whole sequence here a trial. So this whole thing is 4 plus 2 is 6 times 2 is 12 seconds long. So the time between the beginning of one stimulus and the beginning of the next stimulus is 12 seconds. So the first stimulus occurs at 1 second. So stimulus 1 is at 1 second. Then stimulus 2 is going to be at 13 seconds. Likewise, response 1 is going to be, you're just going to add 4 plus 2. So 1 plus 4 plus 2. So the 4 is the fixation, the 2 is the duration of the stimulus. So that's at 7. And the second response, Q would be at 13 plus 4 plus 2. So this kind of highlights how we're going to code this up. So the stimuli are always 12 seconds apart. So in Matlab land, you could write that as 1 colon 12 colon, and we're going to have a total of 200 seconds. Whereas the response cues are always 6 seconds later. So we're just going to take the stimulus time plus 6. Actually, I'm gonna write it. You'll see why in a little bit. Plus 4 plus 2. Later on, we're gonna be more flexible about that 4. Okay, so hopefully that's clear. Let's find Matlab. That's not Matlab. Here's Matlab. Okie dokie. So, right, so we drew the timeline. How much time passes from the beginning of one stimulus to the beginning of the next? 12 seconds. We just drew that out. The first stimulus is at 1 second. When are the rest of the stimuli? We just do, this is just what I wrote out, 1 colon 12 colon 200. So the length of our run, it'll be 200 seconds. And then to get the time that the response cue occurs, we're just going to take the 1 colon 12 colon 200, add the 2 seconds, this is the duration of the stimulus, and then add 4, which is the fixation. How many stimuli can we fit into a 200-second long run? You can do the math, figure that out. Is 16. Must be 200 divided by 12. Yep, it's a little over 16. We can fit 16 in. All right, so here is the code. Also, Pal, I think the microphone on my iPhone headsets are, I think it's starting to go. So sorry for any weird kind of staticky thing. I'm going to get a replacement for that. Okay, back to the code. So I don't think we've created regressors here before, but I also don't recall if I've talked about this, but whenever you're applying convolution to create a regressor, you don't want to convolve in the same time resolution as your data. If I use a 2-second time resolution, it can't really differentiate between anything that happens within a 2-second time point. You tend to miss the peak. I can say more about it if you have the book that I co-authored. There's a whole blurb about it in there. But anyway, we always use a finer time resolution. SPM uses your TR divided by 16. I just used 0.25 here. So this TR is the TR. We're assuming a 2-second TR. This T here is basically just a time vector in the resolution of the convolution space. And then I create the appropriate HRF using the SPM HRF function, which is in the directory I supplied. So we can have a look at that. What? Oops, oops. That's weird. Computer switch screens. Where's my plot? Uh-oh, here. Ran the same wrong code again. There it is. All right, does that look familiar? It should. That's our friendly double gamma HRF. If you're an SPM user, that's what is being used. Okay, so now to create the regressor, I'm starting with, I should use S, but T1, this is just the first regressor. These are the onset times. As I said, we just need to do 1 colon 12 colon 200. If you're not familiar with Matlab, all that's doing is counting in increments of 12. So I start with a vector of zeros, and then I'm going to go in, and for each stimulus, I'm going to fill in ones within the range starting from the beginning of that stimulus until 2 seconds later. So the 2 seconds is because, as I stated above, we are assuming a 2-second long trial. Then I convolve it, and then I sample it down to the TR resolution. All right, so that's all this is doing. There it is. There's our first regressor. Beautiful. So that's for the stimulus. And now this is just a vector for time in the resolution of the TR for plotting purposes. And now I'm just going to do, real quick. Now I'm going to create the other regressor, which is for the response stimulus. So start with a vector of zeros again. The times, remember, we said you just add 2 and then add 4. So this vector will be the times for the response stimulus, and then the same thing for convolution. And then I just mean center the 2 regressors because you can either mean center or you can put a column of 1s in your design matrix. Totally equivalent. I am just mean centering. That's what FSL does. Notice we're not modeling data. If you're modeling data, you have to mean center your regressors and your data in order to take out a column of 1s in the design matrix. Okay, and we can plot them. There they are. So the blue is for the stimulus, the green is for the response. Looks pretty good. Anyone know why these 2 are higher than all the rest? Think about it. If you can figure out why these are all lower than these, post it on Facebook, in the Facebook group. I'm pretty sure I know why that's happening. Okay, so now if you'll recall, I didn't review the efficiency calculation because I was assuming you watched that video, the one prior to this. All we need is our design matrix and our contrast, and then this equation that's coded up here is the efficiency for the first contrast, which is just the stimulus alone. And then the second one is the contrast that gives me the efficiency for the response regressor. So I'll run those. We'll look at them in a little, well, I'll look at this one right now. The efficiencies are going to be really close. It's around 0.6 approximately. Now you might be wondering, well, is that good? I don't know. Efficiency doesn't have a threshold. It's not like a power calculation. Efficiency only allows you to compare designs to each other, assuming you have the same length of run. If you start making the run longer or shorter, your efficiencies between your models will not be comparable. And then we can also do this style of efficiency where you're basically pulling over the 2 contrasts. You can do that as well if you'd like. It really depends on what you're doing to optimize your model. I'll show you a way that I do it at the end. Okay, so that's that. You might be wondering, well, why do we do that? Well, we did that so that we would have the efficiencies from the fixed ISI to compare to a design with jitter. So to jitter, typically what people use is a truncated exponential. And instead of forcing you to wrap your head around what a truncated exponential is, FYI, I think a lot of people don't generate truncated exponential data properly. There's code for it at the very bottom, and they also don't report it well. You should always report what the mean of your truncated exponential is, not the mean that you had for the values you sampled, but the theoretical mean. So all that is below. And that I'll get off my soapbox about truncated exponential stuff being not reported well. It only matters if you're trying to repeat what somebody else did, but you have no clue from what they reported what parameters they used. Okay, anyway, I'm going to use a uniform distribution to sample the ISIs. And basically what I'm going to do here, going back to this, so remember we have our stimulus. This will always be 2 seconds. And then we have our fixation, our response for two seconds, and then another fixation. Basically, what I'm going to do is all I care about is if this plus this is a grand total of 8 seconds. So what I'm going to do is I'm going to randomly sample this one. We'll call this fixation 1. And then this one is always 8 minus fixation 1. I'm not saying this is a great design. This is mostly an illustration to show you how to do this. But yeah, it works fine for here. I'm not saying it's a bad design, but there might be reasons why you wouldn't want to do this. So what we're going to do is fixation 1. I want it to have a mean of 4 seconds. And I'm going to use a uniform distribution to sample it. So I'm going to have a range of values that are equally likely to be chosen for the first fixation. And I want to make sure, often you have some type of limit, like I don't want these two things to be a half a second away from each other. That's too close. So we might set the minimum equal to 1 second. So the uniform distribution, pretty easy distribution. So if you have a uniform AB, that just says that if you plotted it, the distribution, all values between A and B are equally likely. So you get something that looks like this. The mean of a uniform distribution is equal to A plus B divided by 2. Okay? So the mean's really easy to calculate. So here, in this case, we want our mean to be 4 seconds, the min to be 1 second. So you kind of just reverse engineer this. So the min is, say that's A. So we have 1 plus B over 2. We want that equal to 4, which implies 1 plus B equals 8, which means B equals 7. So we want to use a uniform 1, 7. Now Matlab only has a uniform 0, 1. So what we're going to do is we're going to take a uniform 0, 1. We're going to multiply that by 6 and add 1. So if you do the math, you get 0 times 6 is 0 plus 1 is 1. And 1 times 6 is 6 plus 1 is 7. So it will work out just fine. Let's go back to Matlab. Easier said than done. Come on. Here we go. All right. So I'm just working that out here. So all I need to change is the onset time for the response stimulus. I'm keeping all of the stimuli the same. So the onset time and the stimulus is the same. The onset time and the response cue, I'm going to move that around to adjust the ISI. So T2B is replacing T2 above, which was the second regressor. And this is that uniform I was telling you about, uniform 0, 1. I multiply it by 6 and add 1. So that is now my ISI. So this replaces the 4 that we had before. On average, this will be 4. But we're going to add 2 to it, again, to account for the fact that the stimulus was 2 seconds long. All right. That's the only thing that's different. The regressor is otherwise created exactly the same. And then I just create my new regressor. Oops, we're going to plot run all these guys together. It's creating the regressor, and then I'm going to plot the old with the new. And there it is. So actually this is in the book, this figure. Not exactly because things are random, but this illustration's in the book. So now the random time is not between, the labels are wrong. This is 4 seconds. This is between 1 and 7 seconds. We just established that. So on average, the ISIs are the same in these two. Okay, it's going to drive me crazy. Let me go fix it. So this will be right in your code. 4 seconds between 1 and 7. Only wrong for me. Okay. So on average, this interstimulus interval, or this fixation, sorry, will be 4 seconds, the one between the blue and the green. Likewise, on either side of the green, it'll be average of 4 seconds. It's just jittered now. Okay, so now I'm going to compute the efficiencies, same equations, and we're going to compare them. and look at the correlation. So here we go. The jittered efficiency is 1.2, where the fixed efficiency was 0.59. That's a pretty big increase. That's double, right? 0.59 times 2 is 1.18. So this is over twice, the efficiency. Well, at least for this first contrast. The second one's almost twice as big too. Anyway, the point is there's quite a boost in efficiency. So this means your variance for the jittered model, your within subject variance, will be half as large than it will be if you use the fixed efficiency. Granted, we all know from the mixed effects model lecture that I gave that the between subject variance typically dominates, and it's bigger than the within subject variance, but it certainly helps to have a more efficient design. And I also computed the correlations. That's what we have here. We have a correlation of negative 0.855 for the fixed design and negative 0.64 for the jittered design. When you jitter, your correlation will shrink towards 0, which means good things for your regressors. All right, so in reality what you would do is you wouldn't just do one jitter and take that, because even within the jittered design there's variability. So you would test a bunch of jitters. The one thing wrong in this code is I should have created a matrix to save out the ISI information so that when I choose the best design I can actually still access that information. So here I'm just going to run 100 simulations for illustration just so you can see how much the efficiencies change. Right, so here they are, and this is what I was telling you earlier. So instead of using that, man, I'm blanking, the efficiency where you combine the two, in this case, since I'm only interested in two contrasts, what I've done is I've plotted the efficiency of one contrast against the efficiency of the other. So there's quite a range here, efficiency between 1.2 all the way up to about 1.9. So that's a pretty big change. So you would want to select from the designs up here, and obviously if I ran more simulations there would be a wider selection to choose from. Just to let you know, so let's say you have 3 runs that you're going to use. So you're going to have each subject perform 3 runs of a task. I highly recommend you have more than 3 designs. It'd be nice if each subject had their own randomization. Obviously that's not always possible, but pick more than 3 because I'm finding in some of the work I've been working on that even though you did do things randomly, there are certain patterns that can cause biases in your result. I'm not going to go into that now, but just again, instead of just choosing 3 random designs, choose, if you can, 1 for each subject, or I don't know, just a ton of them. Okay, and you can do the same exercise, but with changing the trial order. The code will need to be overhauled quite a bit, but you get the idea. You have the code now for creating the regressors, and you can do that, and you can also see how the efficiency changes. Last, here's how to properly code up a truncated exponential, and this is just how many simulations I'm going to do. This is the lambda parameter from an exponential, so often people will report that in this, but then they don't actually generate the data properly. But this is the max value. So this would be a cutoff of 5 seconds, and this is related to the mean. It won't be the mean of your truncated exponential. This is the true mean of a truncated exponential. So for these settings, the true mean is 2.0994. This code generates the truncated exponential values, and you can see I'll verify that the mean is right. 2.0966. That's with, I don't know how many simulations I did here, like 1 million or something. But anyway, hopefully you believe me. And this is the proper code for doing a truncated exponential. You don't just necessarily simulate a bunch of exponentials and throw away the values that are too big. Okay, I think that's all I have. Let's see if I had anything left in PowerPoint. That is it. This one ran a little long, but it's just a long illustration. Thanks for your time and your attention. Please feel free to join the Facebook group. Link for that is down in the info box, and have a wonderful day.